Okay, we're going to look at this in this YouTube at the applications of parabolas. So how do they apply to the real world? Whenever you see this word applications, it's now talking about taking maths into the real world, which is not always easy to do. But with parabolas, actually, there are some applications, and they have to do with things like balls being thrown upwards, because gravity will take the ball down. So a flight of a ball or any sort of projectile generally takes on a parabolic shape, and then we can model it with an equation, and then we can therefore find out things like, what's the maximum height, how far did it travel, all this sort of stuff. So applications of parabolas. We're in exercise 7F. We're on page 461, and I'm looking at question 1 from that exercise. Just to get us started, I'm going to have a look at another example as well, if we have time. So, okay, just read through this question here. A ball is thrown upwards from ground level and reaches a height of h meters after t seconds, given by this formula. Okay, so have a little think about that. Sketch a graph of the rule for t is 0 to 4 by finding the t-intercepts and the coordinates of the turning point. Right, so sketch a graph. We need to sketch a graph of this here. Okay, so it's going to look something like this, except we're going to have some axes, aren't we? So we're going to have a, let's have a, what's that axis going to be? Have a think about that. And what's our horizontal axis going to be? So h equals, it's normally y equals, isn't it? And what do we stick on the vertical? We stick y. So this is going to be our height, and that makes sense because the ball's doing this, so we want to see our height up here. And if that's the height, then this is going to be our time, t for time. Normally this is the x-axis. So we're changing our letters around. Hopefully that's not confusing you. Now we need to sketch this. Now you could get your graphics calculator out and do that, but I reckon this is pretty easily done algebraically. We can just make, as we have been doing, how do we find, we're going to 4 on the t-axis by finding the t-intercepts and the coordinates of the turning point. So let's find the t-intercepts, or where h equals 0, because when h is 0, we've got our t-intercepts, haven't we? So let's solve for h equals 0, so it's 20t minus 5t squared equals 0. Now this is 4 t-intercepts. Just make that note in brackets. Solving this, now look, we've just got 2 terms, so remember we've just got 2 terms, take out the highest common factor, don't we? So the highest common factor here looks like, to me, we've got a 5 and a t that probably goes into both. That means I bring inside my bracket a 4 minus t equals 0. Look at that. That's 20t minus 5t squared. That looks good. Now if we solve this, we get 5t equals 0. So that's t equals 0. We're using now the 0 factor law here, aren't we? 5t equals 0. Solve that, so t equals 0. 4 minus t equals 0. What's the value of t here that makes 4 minus t equal to 0? Well, that'll be t equals 4. So when t equals 0, we're at h equals 0. The t-intercepts. So when h is 0, we get t is 0, and we get t is 4. So I'd say what's happening here is that it's going up and down. That's my 4 there. That's my 0 there. That's a model of this graph. Now you can see it's minus 5t squared, so it is a sad face, concave down. So that's a sketch of the graph from t equals 0 to 4, and we got that just by factorizing and making it equal to 0. Coordinates of the turning point. I haven't got that yet. How do we get the coordinates of the turning point? Right, so what do? We go halfway, don't we, between the t-intercepts. So it's always halfway. That's our axis of symmetry, because these are symmetrical things. So we'll drop in down there. That's 2. So what's that value of h going to be? Remember, this is not to scale, so don't bother counting squares here. But we can put 2 in for t into this equation, can't we, to find out what our turning point is. So I'm going to do that piece of work over here. So when t equals 2, alright, we get h equals 20 times 2 minus 5 times, putting 2 in there, 2 squared. So let's go, 20 times 2 is 40, minus 5 times 4. 5 times 4 is 20, isn't it? So that's 20. So when t is 2, h is 20. So I'd say that's a 20 there. My turning point, therefore, is at 220. Okay, that's the coordinates of the turning point. So the question B in this in here is what maximum height does the ball reach? The maximum height there is there, isn't it? On my turning point, maximum height is 20. So B, the answer to B is 20. But what are we in? Are we in, because we've put this now into a real life problem, there's going to be things that we can talk. We can say meters here. 20 meters is the answer to B. And this part C says, how long does it take the ball to return to ground level? Okay, this is seconds here. It looks like we're going all the way down here, aren't we, to 4 seconds. So the path of the ball is such that it goes as high as 20 meters after 2 seconds, and then it's back to ground after 4 seconds, all dictated by this rule here that links the height to time. Okay, let's have a look at another example. I'm going to go over to page 460 and look at the example 13. I might not get through this whole example because I don't want this to go on for too long, but I'll pause and I'll write it out. Okay, I've written the example out. It's a piece of wire 100 centimeters in length, so we're going, this is a very common question, this is why I wanted to do this. It comes up in the exercises question 5, so you'll probably end up doing a question very similar to this. So we have to set up the equation here. In this question here, we had the equation given to us. In this one, they're giving us some information, we have to set it up. So, piece of wire 100 centimeters in length. Let's draw that piece of wire. There it is. It's 100 centimeters in length. Is bent into the shape of a rectangle. So this is going to be bent up. Now this goes to this. Right, but we now know what the perimeter is, don't we? Because we're using that 100 centimeters. Let x centimeters be the width of the rectangle. All right, so let's do as we're told and put x centimeters there. That's the width of the rectangle. Okay, now if that's x, what we want is an expression here for the length, don't we? So if that's x, I know that this is x centimeters. I should be putting centimeters in there. Centimeters in there. So if I started with 100, all right, let's go back up to here, and let's say we chopped off x here for the width. So one of my widths is x, the other's x. What is left here? What is left? How many centimeters do I have left for these two lengths? So I had 100. I've used up 2 x's. So is that 100 minus 2x? So have I got 100 minus 2x centimeters now between these two? So would that be, if I'm gonna divide that by 2, is that 50 minus x for each one? So let's just think about that. 50 minus x plus 50 minus x. Does that work? 50 minus x, 50 minus x. Does that work for the lengths? If we added all this up, would we get 100? So add up those two, 50 minus x plus 50 minus x. Is that 100 minus 2x? Yes, it is. And we add the x and we add the x, we're back to 100. So now I've got my rectangle all in terms of x. The dimensions are out there in terms of x. Now, what we can do now is have a look at the area. Right? An expression for the area of the rectangle is length times breadth, so that's x by 50 minus x. Alright, what might have been an easier way of looking at this, actually now I'm thinking about it, is if I make x my width, then if we just look at two lengths of the rectangle, sorry, the width and the length, just half of the rectangle, then I know that this plus this has to equal half of my 100 centimeters. So I know that, right, this x and this length have to equal 50 centimeters. So if that's x, then this is 50 minus x. And obviously if that's 50 minus x, so is that. That might have been an easier way of explaining that through. So either way, my area now is x by 50 minus x. And that we can then look at graphing that area again. So we'd have on our horizontal, vertical axis. So now we're getting into the modeling phase of this. We have a look at our area here against our x here. It's already factorized, so we can work out what the intercepts are by making area equal to 0. So if we make the area equal to 0, we've got x by 50 minus x is equal to 0. And solving that gives us x equals 0 or x equals 50. So it's a concave down, it's minus x squared. So it's doing something like this. 50 to 0. We would therefore find out that our maximum area is achieved when my value of x is 25, halfway between my x-intercepts. Putting 25 back in here, we would find out that my maximum area, so my maximum area, which is the point of the question, is at 25 times 50 minus x, which is 25. So 25 times 25 can be worked out there. I think that's 625 off the top of my head. And let me pause and see that. Okay, so that is right. So the maximum area is 625. In this case, we're talking about centimeters squared, aren't we? And the dimensions of the rectangle that we made out of this 100 centimeter piece of wire are 25 by 25. So in fact, it's a square. To maximize area, it's a square. Okay, so that's all I'm going to mention in this YouTube. Exercise 7F is the exercise on this applications of parabolas, so we'll have a go at that in class, and no doubt we'll work through some problems together. So I'll see you soon.